Hello, my name is Anthony Pepitone, and this is Web 4 Circuits Literally. So with this lab, we're literally going to be examining the different ways in which components in the circuits work, and we're also literally going to measure the current throughout these exact circuits. So we are going to have to use some fundamental principles of energy conservation and current conservation, which basically is saying that literally it's going to be zero as you go around the current one for loop. Along with this, the brief preview of the results says that the current will result in a 0-volt change after completing one full loop, and the current will take the path of least resistance, and finally that the capacitors will only allow the current to run until they are fully charged, and then they will stop literally. Literally, the main equations we're going to be using is Ohm's law, which says that V equals IR, and energy conservation, which we derive a couple other formulas from later, literally, but Q over RC plus dQ over dt equals 0 is the other main formula that we're literally going to be using. First things first, we started off with two 1.5 volt batteries along with two ammeters, a 47 ohm resistor, and a 100 ohm resistor, literally. From this, we predicted that the ammeter would read 0.02401 amps, but in reality, it actually literally equaled 0.02 amps. And when in reverse, it read that it was going to be negative 0.02 amps. So after we add the voltmeter, we can see that the voltmeter reads 3 volts, and that's because literally the batteries are combined to equal 3 volts. Like, if you can't tell that, I don't even know. You're not even good at Fortnite, probably. And the ammeter reads 0 amps because the circuit is literally open. There's no current thrown through a voltmeter. Next thing we had to do was take a hell of a lot of pictures. And the first picture shows between the batteries is 3 volts, as we discussed before. That's literally double voltage of the batteries. All the other ones are basically zero, but between the first resistor is negative 0.96 volts, and between the second resistor was negative 2.04 volts, literally. After that, we made a graph of these findings, and we saw that between C and D, which was the first resistor, it went down a little bit, but between E and F, it had a big drop because of the 100-volt resistance, bringing it all the way back down to zero. In between my victory royales, I predicted that it was going to be zero because of a conservation loop rule, which says it's going to be zero. And I literally found this to be true. Like, I literally knew it. And 3 minus 0.96 minus 2.04 literally equals 0 volts. So the ammeter also doesn't change because there's no actual current flowing through the voltmeter, as we already know. Next, we put ammeter parallel to the 100 ohm resistor, and literally, because we know that circuits take passive least resistance, it's gonna make the ammeter read 0.06 instead of 0.02 because it goes around the resistor and it doesn't even resist. So I calculated the resistors and it was a little different, and I'm not really sure why. I think it might be because we're not counting any of the resistance from wires or potential ammeter resistance because those are zero. But we found them to be 48 and 102, which is a little bit off from 47 and 100, literally. Next, we made a circuit with a capacitor and a light bulb, and we saw that when you connected the circuit to a battery, the capacitor charges and the light bulb lights up, but only for a little bit, because once it's charged, the circuit stops working. But once you disconnect the battery and run the circuit, the opposite happens and the capacitor discharges literally. So for the 10 Faraday capacitor, it was literally freaking 9 seconds. And then it doubled for the 21. It went to 16 to 17 seconds literally. Also, we're going to be using this equation on the left to calculate literally the capacitor and how long it takes to discharge throughout the circuit. Literally, we'll find that out. So we plotted volts first time as we did ln of V over V naught, and literally what that gave us was a negative slope, and we saw that negative 1 over RC in this experimental data literally gave us 5.98, so freaking close, but the actual was only 6, so we were a little bit off. I'm not really sure why. So what if we were literally doing this lab in real life and we use an actual ammeter instead of a simulated ammeter? The real one's a little bit different because there's some freaking resistance. And how would this affect the circuits? The current that's measured would be a little bit less than the actual current, literally, because the ammeter has some freaking resistance. And if we were doing this in real life with a real battery, a real capacitor, and no resistor, ideally, the model of the capacitor would instantly charge super duper quick because there's no resistance. but this doesn't actually happen in real life, literally, because the wires and capacitors have some freaking resistance, which would slow down the time it takes for the capacitor to charge. Guys, I hope you literally have a freaking epic spring break, and I hope you get #1 victory royales all over spring break. Bye bye, dudes.